Okay, so now we're going to be talking about the different kinds of power that exist in circuit analysis as well as power systems. With the introduction of AC, we get different kinds of power. One of them is called average power. P is equal to VI cosine of theta. We then have reactive power. Q equals to VI sine of theta. If you notice, they both share the same quantity, which is, in the case, apparent power. So P apparent is equal to VI. The combination of the two joins complex power, which is S equal to P plus JQ. Now note that within this, there's other things we can actually derive from here. If we take the ratio Q divided by P, VI will cancel out, and we'll get sine of theta over cosine of theta equal to tangent of theta, or that Q is related to P tangent of theta. Now, later on, there's also something important for us to talk about, and that is the case of power factor. So, the quantity, let us look at this quantity. Cosine of theta is called its power factor. But within that power factor, we can't just simply say power factor because the angle tells us it has to be in reference to something. So we have to say followed by leading or lagging. And if you recall, in the case that the angle is positive, it is lagging. While while this angle is leading. Like so. Now, it's important for us to emphasize that finding power factor allows us to deliver the maximum amount of power while not absorbing any power that could be wasted. In other words, power must go high and Q must go low, so that our complex power is the same as our average power. Now, we can also express this in polar form as the quantity S angle theta, where the magnitude of S is equal to the square root of P squared plus Q squared. Now, that's just the different kinds of power that exists. To kind of practice on this, let us give some quantities. So let's say that I delivered 100 watts of power. Oh, actually, before I give an example, let me talk about the units. So for power, we use watts. For reactive power, we use volt amp reactive, or VAR. For apparent power, we just use volt amp. And for complex power, we have no unit. So I'm going to put kind of quotation just to say nothing. So now from here, let us probably talk about a few things. So let's say I delivered 100 watts at 25 volts and 25 volts max with 1.2 amps of current max. Find PF. From here, it's just as simple as really using this formula and just plugging it in. But one thing just to kind of keep in mind when with problem solving for different kinds of power, look at the units. Here, units would be very important. If this didn't say watts and I just told you, you know, 100 power is delivered, you will never be able to tell what I'm talking about. 100 watts, 100 var, 100 volt amp, 100 nothing. I won't be able to really tell you. So we have to specify the quantity unless we are specified that it's complex power. Then in this case, this would refer to the magnitude best. But let's not assume that. Let's assume because it says watts that we're talking about average power. P is equal to VI cosine of theta. The power factor is right here. So all we really need to do is find this relationship. So we get 100 watts divided by 25 times 12 over 10. This is 1,000. And then 25 times 12 is 250. So it's going to be 300. So you get about, oh, I don't know, you get like 3.33. So what does this tell us? This tells us that I cannot pick any kind of quantity because I might get very illogical quantities, values that don't necessarily make any sense. Oh, so a power factor of 333 means we actually have a system that somehow generated more power than it put in. So this is invalid. So keep in mind that I can't necessarily pick just any kind of quantity or any kind of value because I might end up with an illogical number. Now, just to kind of describe to you the idea, cosine of theta describes power factor. If power factor is 3.33, this is outside of the range of -1 to 1. So if I asked you, find the angle of this, you wouldn't be able to do so. So let's maybe adjust the numbers a little bit. Let's say it gives us, let's say 120 volts, or even better, not instead of 25 volts, 250 volts. Now this quantity becomes 1,000 over 3,000, or zero point 0.03. That's okay. That's more reasonable. It's not close to 1, so it's not that efficient, but it's okay. Now, what if there's one more information I need to tell you? Leading. If I don't tell you that this you might not be able to really describe what power factor you're given. So we get power factor is 0.33. So therefore 0.33 leading. And there we go. So in summary though, when you're given example problems, try to practice boundaries with some of this because not all quantities make a lot of sense. in terms of AC analysis and AC power. So if you chose a few examples and the number kind of seems off, you can always verify it this way. Power factor is always less than or equal to 1, but it could be 0 as well. It cannot exceed that range. When angle is greater than 0, you get power factor lag. When angle is less than 0, you get power factor lead. And remember, this is in the case of inductive systems. And this is in the case of capacitive systems. Okay? So, all right, thank you.